So today we will cover this chapter 17. We finished till chapter 16 last time. Chapter 17 talks about context-free language. It is so here we have this theorem. It says that if you have two languages, language 1 and language 2, and let's say we know that both languages are context-free language, and then if we apply uh, concatenation, sorry, the if we want to combine both languages, union of two languages, the resultant thing will also be a context-free language. So in other words, when you have two languages, so they are closed under union, concatenation, and clean closure. So what it says, if you apply, so this line means the last line, this line. So it says that if you have two languages, and if these two languages are context free languages, and we have this information, if you apply union there, or if you concatenate them, or you if you are interested to find the closure property of that, so all the resultant thing will be a new language, but it will not change the behavior of this language, and the resultant thing will also be context free language. This is what does it says. So now we will see the uh, L1 plus L2, that how we can say that. So now if you see this, we have two languages here. One is L1 and one is L2, and we are trying to prove this for L1 plus L2. And these are two different languages. And L1 is represented by G1, which is context-free grammar for this context-free language. L2 is represented by another grammar, which is G2, which is a completely different language, but it is also context free language, and it is L2. So then how we combine them, what is the process that you apply the union of this one. So the idea is this, that each non-terminal x, so assign all the non-terminals of one language with numbers, and the other language with another number. So then if the non-terminals are same, so at least you know that this non-terminal belongs to language 1, this non-terminal belongs to language 2. Let's say all non-terminals of language 1 will be numbered as 1, and all non-terminals of language 2 will be numbered as 2. So then you can get idea that this non-terminal belongs to which language, like either language 1 or language 2. And then you have the start production rule. Add a new start production rule. uh, S can be replaced by S1, S can be replaced by S2, and just add that into your grammar, and the job is done. So look at, see this example, and then you can get better idea that what we are saying. So I have one context free language. This is palindrome, and this is the grammar for this language. So how many production rules we have for this language? We have one production rule, second, three, four, and five production rules. And all production rules are start production rule, start with S. And then we have another language, which is this non-regular language. And this is grammar for this language. This language has two production rule, 1 and 2. And now I want to combine these two languages together by union. So we want to create a new grammar which can accept all valid word of this language, and which can accept all valid word of this language. So instead of having two grammars, you want to entertain both languages by one grammar. So how we do that? So first of all, this first language, its grammar, context free grammar, I will numbered all of its non-terminals with number 1. So now look at this one. So we have this grammar here for the for language 1, and we numbered all of its this production rule by S1, 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 and all just non-terminals. and then we write the second language here, and we numbered all of its non-terminals by 2. So then we get idea that this is language 2, S2, S2, and everything. Not just non-terminals, okay? Because terminals will not no need to number the terminals, just non-terminals. And then we add a new production rule which was not there, and we are saying S can be replaced by S1. Look at this one. And S can be replaced by S2. We add two production rules by a new S. So this S is a new non-terminal we introduced, and S1, S2 are the existing non-terminal. So what we want to say here, if you wanna go to this language, so you can adopt this production rule. S can be replaced by S1, and then later S1 can be replaced by anything of this, and you can achieve any word from this language. Or you can, if you want to achieve or create or derive another word from this language, so then you can use this production rule, and then later you can substitute this production rule by any one of this, and you can create or derive any other word belong to this language. So this is a very easy process. You should understand that how we can do this. So what we are doing, we are just numbering each grammar with the unique numbers, and then we add this production rule by or sign here. Or sign, it's not and, it's or. It means you are adding two production rules. So what does this production rule mean? It means you want to write something like this: S can be replaced by S1, S can be replaced by S2. So in short, we can write this way: S can be replaced by S1 or S2. It is the same thing. Okay. So we add this one. So look at this one. Second example here. We have this one grammar, which has two production rules, and it has three non-terminals S, A, and B, capital B. Oh, sorry, this is whole thing is one grammar. And then we have another grammar, second grammar, which is this one. It has only one production rule: S can be replaced by lambda. So now we follow the same method. First we numbered our first grammar with number 1, S1, A1, B1, A1, B1, and the second grammar with S2 can be lambda, and introduce a new production rule: S can be replaced by either S1 or S2. And this way you perform this union operation in two context-free languages. Any question, guys? This is pretty straightforward. It's not hard. It's easy. You are not doing any sophisticated job in this. Just you are adding a new production rule and combining two grammars by that production rule. So now, if you try to see relate that with what we done before, so look at this one. So we have one TG, FA, or something. Let's say something like this, and these are two different languages. And then we add a new state here. We connect this with lambda. We connect this with lambda, and now these two machines are connected by one machine. So exactly what we are doing here is the same thing, that we are adding basically two um, new production rule by S, and this is a start production rule. So now how we prove this by machine, actually what machine is doing. So look at this. So we have, this is our first grammar, this is our second grammar. So how we know that? We have this solid line here, we have these dotted line here. We combine the start state of both by this way, and we have this final state of first grammar, final state of second grammar. We combine both edges with by to the new accept state. So exactly this is what we are doing here. So now if you see this, we have these are two machines. This is our one machine, and this is our second machine. And what we did, we combined the start state of this one and this one together. Look at this. We have one start state here, and this goes here to the read, and this goes here to this read. Look at this one. This goes here to this read, and then from onward here we have the same machine. From onward here we have the same machine, but where you have this accept state, so this A goes to this accept. Look at this one. This A goes to this accept. Instead, you have a second accept, so you connect this with this one, and this is A. So you connect with this one, and this is A. So this is very easy. You just merge the start and the final state of both machines without changing any or without deleting any label of the edge or the edge, and you will get the L1 plus L2. So physically, when you have two machines, so how you deal with that for L1 plus L2, this is very easy example of that. Easy, it's not hard, huh? So now we see this thing, and now let's say if we are not doing union, if we are doing concatenation, so how we perform concatenation on grammar and on the diagram on the on your this PDA. So for it will be the same idea, 100% same concept, the way you deal with S1 plus L2. Only difference is when you add a new production rule in union, so you add this new production rule. You are saying S1 or S2. Whereas here you will say S1 dot S2. So here you need to know that, so in this case, or in this case, order does not matter. But in this case, order matter. You should know that from which machine, from which grammar, from which context-free language you want to start and where you want to finish. So you need to know this, okay, from where you start, from where you finish. So now and because of that, from where you start, so that grammar start production rule will be in the leading position. Where you want to finish, that grammar start production rule will be in the following position. So now, for example, we have a language. This language will be, it's a context-free language, and it is represented by context-free grammar. And this is the grammar for that. And if we see, it has 1, 2, 3, 4, 5 production rules. All are start production rules. It has only one non-terminal, capital S. And we have another grammar, which is this. It has two production rules and only one non-terminal S, and both production rules are start production rule. And we are interested in, and let's say this is L1 and this is L2. So we should know that which one is L1, which one will be L2, because it matters here. So now we are interested to combine these two grammar, and we want to create a new machine which will accept all words that start with this language and end with this language. So we created, so we assign exactly the same way the unique numbers to language 1 and unique numbers to language 2. Look at this one, S1 1 1 1 here for all non-terminals, and 2 2 here. And then we add this new production rule. S can be replaced by S1 S2. So this is the only difference in the start production rule. Otherwise everything is same as you did in union, but now here in concatenation it is just like, instead of or, you add dot here implicitly. It has dot there. And beside, in case of union, order does not matter. In case of concatenation, order matters here. If you write S2 S1, it means you want to start from language 2 and you want to finish at language 1. So order matters here. I hope you understand this thing, and it is not hard. Now let's move to the next step. If we talk about the clean start, so then it means that we have a new grammar. Um, so we have a grammar and we want to find the closure property of that grammar. Okay, clean closure properties. How we do that? So again, you need to add this new production rule here. So S1, S and the lambda, because when you have star, it means that the grammar should accept lambda, whether it is accepted by initial machine or not, but the new machine should accept lambda. So we for that we add explicitly one production rule, S can be replaced by lambda, and then exactly the same thing, that the machine can concatenate with itself and it can generate as many words as you want. So S1S. So now if you have grammar here, let's say we have this grammar, and if you see, this grammar has 1 2 3 4 5 production rules, and all production rules are start production rules, and all it has only one non-terminal S. So now, I mean, you can follow the tradition the way we did last time. So you can say that um, I want to assign this as 1. Let's say a S1, A, S1A, B, S1B, A, B, lambda. And then you want to say that second one, I just want to keep S2 or S. It is the same thing, does not matter too much. I just want to keep as the original, because here when you are concatenating two languages, so one language is concatenating with itself. So S is concatenating with itself. So that's why we keep S as it is. And then we have this S1, oh sorry, not one, SA, B, SB, A, B, lambda, and you add a new production rule. You are saying, I have a new production rule S. What does it? And S can be concatenate with, so here order does not matter because both languages are same. So either S, S1 or S1S, it is the same thing. And or you add a new production rule because you wanna convert this into clean star, which is and it should accept lambda. So we are saying that lambda. So exactly the same concept, but here you are concatenating the same grammar with itself. So you are saying S can be replaced by S1 as here, and then original grammar as it is. Combine these two grammars, so implicitly it has dot there. So here order does not matter. Either S1 can come first, S1S or SS1. It is the same thing because both grammar are same. And then you need to add with or this new production rule lambda, and the job is done. So by clean star, so this way you can implement the closure property on your context-free grammar. And exactly, so now sometimes if you see here, instead of giving a new, when we give the numbering, so we want to create a new identity of that non-terminal, that this non-terminal does not belong to this language, it belongs to a separate same language but the different instance of that. So either you assign a number or you change its name, instead of S to X, Y, Z, any, but it's better that go with the numbering, because when you change the name by to any other letter, so might be it create any mistake, or there is a more chance probability of doing a mistake there. So this is good practice that in the subscript you change the add the new number there. So this will be easy thing. But here, if you see, we did the same thing. We assign the new production rule, and X can be this, and original grammar is here, and we just add this new production rule and the grammar, and this is, and we replace all S with X. Look at this, and then actual grammar is also here. So we have this thing here. Okay, so this is your closure property. So now we have some facts here. We are saying when you apply intersection, what is intersection? Like S1 plus S2, but not, but this is the, so you know that plus is equal to union also and intersection also. So when, how you get intersect union? The way we did last time, but intersection, when you choose the final state of both machines for the new machine, then you can say this is intersection. So the intersection of two context-free languages may or may not be context-free. So now, what is confirmed? When you perform union, or you perform concatenation, or you perform clean star of two context-free languages, the resultant thing will be, for sure, without any doubt, context-free language. It will not change the behavior of the language. But when you apply intersection of two context-free languages, we are not sure the resultant thing will be context-free, or it may change its behavior. So that's why we are saying it may or may not be context-free. So exactly, when you apply the complement of a context-free language, so may, the resultant thing will be may or may not be context-free. So the intersection of a context-free language and a regular. So now when you apply intersection of a context-free language and a regular language, it's not context-free, so that is just a regular language. So then the resultant thing will always be context-free. Why? Because regular language by self is a context-free language. So it, because it is under the scope of that. So the resultant thing will be context-free language. where we can prove that. So using a PDA similar to the intersection algorithm for the FA. So I mean, for if you have by using push down automata similar to the intersection algorithm of. So I mean, because why it is like this? Look at this one. So if you have this regular language and the context free language is here, so it means that so this language, all these languages are have the same are also come under the scope of this big circle. So the languages which are here are not might not be regular languages, they are different, but this language for sure which is regular is under this scope of this bigger circle. It is inside this, so it means that this also bear all the properties of this language. Okay, so so that's idea behind that. So I think that here we done with this chapter. It's not too big. Any question in this? So otherwise, I move to the next chapter. Any question, guys? So Riley, are you okay with this? Are you happy what we did today? I mean, so far. Very nice. So Nikhil, are we good?
Yeah, we're good.
Very nice. So guys, I hope that you understand this thing. And now if we are good, so let's move to the next chapter. Let me close this, discard the changes. This is chapter, yeah, 17. I already opened this chapter for you. Now let's start the chapter 18. So I mean, main thing you guys done, but this is a very easy chapter. Chapter 19. This chapter is also important. Chapter 19 is also very important. So decidability. So now we will cover decidability. We have some examples of undecidable problems. So these are some questions. We do not have answer of these questions. What are those questions? That are the languages generated by two context-free grammar the same? So we have two languages, language one and language 2, and let's say we have the grammar for this language is G1 and we have grammar for this language is G2. Without knowing what is this language, without having this information that what this language is doing, is there any algorithm that will tell us that these two grammars which looks very different from each other, whether they define the same language or they define the two different languages? So but we are not interested to know what is this language without knowing that information. So is it possible? So we have no idea so far. Whatever the progress science done till today, we do not have answer of this question. Might be it does not mean that this question has no answer. It means that we are not at that level of research that where we can figure out the answer of these questions. So we have no idea whether this question has any answer or we do not know that answer, or its answer exists or its answer does not exist. Solution exists or solution does not exist. It's kind of P and P problem decision. So whether it is a P problem or it's an NP problem, we have no idea about that so far. So this is our decidability issue. These are undecidable problems. So now second question, is a particular context-free grammar ambiguous? We have no algorithm to figure out the answer of this. And I believe that you now have idea about ambiguous grammar and unambiguous grammar. What is that? So given a context-free grammar that is ambiguous, is there another context-free grammar that generates the same language that is not ambiguous? So let's say if you have a CFG and somehow you are able to figure out that this is ambiguous grammar, so are you able to figure out that there is any other context-free grammar exists which is non-ambiguous or which is not ambiguous? So we have no idea about this one, that how we figure out this. Is the complement of a context-free language also context-free? No idea. We have no answer of this question. Is the intersection of two context-free languages also context-free? No idea. Is the intersection of two context-free language empty? We have no idea. Given a context-free grammar, are there any words what are not in the language generated by the grammar? So far, all these questions, we have no answer of that. And beside, we have no idea that does their answer exist or does not exist. So these are undecidable problems. But we do have answer of some questions. What are those questions? So given a context-free grammar, if you have a context free grammar, let's say you have a grammar context free grammar, and let's say it is represented by G1, is the language that it generates empty, means whether or not it generates any word at all. So this is the emptiness problem. So by looking the grammar without having this information, what this grammar define the language, without having the information of that language, can we figure out that this grammar can generate any word, or this is a file language? We can do that. We have a method to figure out. This is called an emptiness problem. Okay, we can figure out by performing that method without going in the depth, in the knowledge of what this grammar represent, what is this language, what this language is doing, what is the definition of this language. We can figure out whether it is a file language or it can generate any single word. We just want to generate one word. If we are able to generate that, it means that it is not a file language. Okay, this is called a emptiness problem. So now, given a second question, given a context free grammar, is the language that it generates finite or infinite? So we can figure out this without having the knowledge of the language, without having the knowledge of the definition of the language. We can say that whether it can generate infinite words or it can generate limited finite words. This is called a finiteness problem. Given a context-free grammar and a word W, so now we have a grammar and we generate a word. We have a word W, and we have no idea whether this word belong to this language or not. Can we say that this word can be generated by this grammar? This is called a membership problem. So we can figure out the answer of this also by using the certain algorithms. Okay, so these three different problems, whether language generates something or empty, called emptiness, whether language generate finite or infinite words, finiteness problem, whether this word belong to this language or not, membership problem. So these are the three problems, and we can find the answer of these problems. We do have the answer of these problems, and we can see that how we find the answer of these problems now in coming slides. Okay. So now, given a context-free grammar, there is an algorithm to determine if the language it generates is empty. So you have a language, you have a grammar, it is a context-free grammar. We can see that how we can generate the whether this language is file language, it is empty language, means it accepts only file, or it can generate any single word. So I will go this process. Let me show you the example, and then you are in better position to understand to this slide. I will come back to this slide. Okay. So now look at this one. So we have this grammar here, and we have, look at this. We have this grammar, and we have no idea that what this grammar is doing, what is the definition of this language. We are only interested to figure out whether it generate any word or not. So how we do that? So the first iteration, you are interested to find those production rules which are just replacing the terminals, non-terminal with the terminals, something like this one. Okay, we have these two production rules. So if we figure out that, now the next step is delete all these production rules. Delete also those production rules which have the same non-terminal like A or B on the left side. So far we do not have. Replace all in this grammar, all non-terminals capital A with small a, all non-terminal capital B with B. This is our second step. So look at this one. This is good. I write this as it is. This is good. I replace this capital A with this small a, AX. This is good. I replace this A with AA. I delete this BY with B with capital small b. this one, and then this one also with BB, and I delete this. And this is my first iteration done. And I reduce my grammar into less production rules, and I move to the next step. So our target is what we want to achieve. We want to convert our this production rule, which is start production rule, all of its non-terminals into terminal. If we convert our start production rule, all non-terminals into terminals, it means this will be a word. So because all terminals will be a word. So when if we are successfully able to generate this, it means that this grammar at least can generate this one word. We have no idea this is finite or infinite language, but this will for sure not phi language. It can generate this one word. That's what we want to do. And now once we did this, we again see, do we have those production rules which are just replaced non-terminal with the terminals, not combination of that, just terminal, non-terminal terminals? Yes, we have this production rule which has just terminals. We have this production rule which has just terminals. So we will delete this production rule. X can be replaced by AA, and wherever you have X, you replace that with AA. Beside, you also delete all those production rules which have X on the left side, because we want to get rid of this. So it means we will delete this production rule and this production rule. And then we do have Y can be replaced by BB. So we replace everywhere Y with BB, and we delete also all those production rules which have Y on the left side. So now the next step will be, I replace X with AA. Look at this. I replace this X with AA. I replace this Y with BB, and also look at this one. S can be AABB, and then I delete all these production rules. Okay, and we successfully transform our start production rule into all terminals, and this will be our one word. And so we can say that our grammar, this grammar can, and this is at this time when you convert your grammar into your start production rule into all terminals. So then you can say that this will stop the process. And now regardless, you have some more production rule left. It's not mandatory that you have to finish all these production rules. You might have some production rules left here, but once your start production rule is converted into all terminals, so then all terminals, so that will be end this process. And because our target is to find a word from here, and we are able to find that, and we can say that this grammar is not a phi language. It can generate this word. We have no idea what is this language, what is the definition of this language. Without having that deep information, that complex information, we just prove that this grammar is not a phi language. It can represent at least some word, which is this word. Okay, that's the idea behind that. And now if you go here, in this slide, you will read, it will just show you all those steps what we just did. So you have this grammar here by the constructive algorithm. So if not convert the, so first of all, grammar should be into Chomsky normal forms, into CNF in the, so like all production rules are either in non-terminal, can be exactly two non-terminals, or non-terminal will be exactly one terminal. And if you see this, all this is into the Chomsky normal form, the grammar. And then you replace, you need to find this kind of production rule if you have that. So replace all non-terminals with its terminal, and repeat this process until your start production rule will be converted into all terminals. And once you reach there, stop the process. Do not move to the next step. That's it. So then you can generate a word. If you are not able to generate that, then you can say that this language is a phi language. It does not represent anything. Okay, so now let's see another example which produce the phi language. So look at this one. So we have this grammar here. First of all this is in Chomsky normal form. Yes. Do we have any production rule which is just replacing non-terminal with the terminal? Yes, we have this production rule. We have this production rule. We need to delete these two production rules. and also all those production rules which have A or B on the left side. So actually we do not have anyone here. So we just delete these two and replace all A with small a, all capital B with small b. And look at the next step. We write the first production rule as it is. A can be replaced by small a. This is deleted. B can be replaced by small b. This b can be replaced by small b, and this can be deleted. And we have this next step. Now we again search that do we have any production rule which is just replacing non-terminal with the terminal or terminals? Yes, we have that. We have one production rule like this. So we need to delete this production rule and all those production rules which has y on the left side like this, and we delete that and we replace everywhere in this grammar where you have y with bb. So now this x can be replaced, this x, oh, sorry, this x will not, this y can be replaced by bb. This can be written as it is, and these two production rules are deleted. Okay, look at this one. We come to the next step. We again search, do we have any production rule which is just replacing non-terminal with the terminal or terminals? No, we do not have any production rule now. This is non-terminal and terminals. Second production rule is terminal and non-terminal. We do not want that. We just want this kind of thing. We are just terminals or terminal, and we do not have that thing here. So it means this will stop our process and we are not successful to transform our start production rule. It's all non-terminals into terminal. So it means that this language is not good. It has not ability to generate any word, and it represent file language. Okay, so that's idea behind that. So now if you see this, oh sorry, it is written here. So terminate step 1 and discover that s is still there. So this context free generates no words. So it generates no words and it represents the file language. So that's the idea behind that. It's not hard, it's very easy. uh, and this way you can find the solve the emptiness problem. Okay, so now let's move to, if you have any questions. No questions? Okay. So let's go to the next step then. So now we are interesting into the parsing problem. So what we are saying that membership issue, that we have a we have a word or sentence and we want to see that are we able to generate this word from this grammar. It's the question membership issue, that whether this belongs to this grammar or not. So we can do that. So now let's say we have this and to do that, we need a parsing, and we will follow the top-down parsing. We start from the start production rule, and we move all the way down, and we try to generate our target word. You know that word will always be at the leaf nodes of your parsing tree. So now we have the word is given to us. We have this word, and we want to generate this word by using this grammar. And we are saying that, okay, how we do that? So now we have these production rules. S can be replaced by E, or E can be replaced by either this or this. Then T can be replaced by this or this. F can be replaced by this or this. So we have almost how many production rules? 1, 2, 3, 4, 5, 6, 7 production rules. And we have how many non-terminals? S, E, T, F. We have 4 non-terminals. How many terminals we have? Plus sign, star sign, parenthesis start, parenthesis close, and small I. So we have 5 terminals here. How many start production rule? We have only one start production rule. So we are forced to start by this production rule. And this is what we want to do now. And what we want to generate, we want to generate this word. So in this case now, when you draw your tree, so you always have, so you choose those. First of all, you should follow the leftmost derivation. You need to scan your word from the left side, and whenever you encounter the first non-terminal, you want to replace that. Beside, you always choose that node which will lead you to the successful generation of your word. So we have the word or the sentence in front of us, and we will choose those nodes of the tree which will suit us and lead us to the final solution of our answer. So now we start from the start production rule, and we are saying because this is the only start production rule, and we use that, we are saying S can be replaced by E, okay, and then E can be replaced by T plus E, and so we are trying to make the complete tree and T. So we, whatever the rules we have, we want to do that. And now here you see you have two non-terminals. You always scan from left to right, and we follow the leftmost derivation, and whatever the first non-terminal you encounter, you just replace that, and remaining part of the sentence will come as it is. So now this T can be replaced by two things, F into T and F. So F into T, and this thing will come as it is. Let me write it more nice so you can see. F into T, and then the plus E will come as it is. And for the second part, T can be replaced by F, and then plus E will come as it is. For T, so same thing here. So T can be replaced by F into T and F. So now again, now we have this is first non-terminal, this is first non-terminal, this is first non-terminal. We replace them to their respective production rules, but we write the remaining part of this thing as it is, because we always do the leftmost derivation. Okay, so now if you see this in the tree structure, look at this one. So I come to here, F into T, and now after that I reach to this thing. And once you reach here, you will notice that now this is taking some shape here. And don't forget that always keep in front for the validity check your word which you want to generate. And which word you want to generate? I plus I into I. So you want to generate this word, I plus I into I. So now if you see this first node, it has parentheses here, and parentheses is a terminal. So now when you have a terminal, it will never be replaced. It means that whatever the word you generate from this thing, it will always have parentheses in the start. The word will have the parentheses there and this close parentheses there. It will never be vanish. So now, so this is wrong thing. We do not have any parentheses in our target word. So it means that if you follow this node, it will lead you to the unsuccessful generation of the word. Okay, and now look at this second one. So it has star here, I and star. So I is good, but star, we do not have star here, we have first plus. It means if you follow this one, this will also leads you to the unsuccessful generation of the word. Same is the case here. Because of this parenthesis, it will lead you to unsuccessful generation of the word. I plus E, it is not complete, but so far whatever it is there, this looks good. So this also is wrong because it has parentheses there. This so far is good. This is wrong. It is good. And this is it finish here. It does not have any non-terminal. So it means I is a final answer, which is not pursue. We will not um, regenerate or go to the next step of these nodes. We will kill these nodes here. We will not continue these nodes, and we will continue only those nodes which will at this stage, it looks that they will lead you to the successful generation of the word. So node number 4 and node number 6, we will follow that. So drop branches 1, 3, 5, 7. I gave you the reason why we did that. Drop branch 8. I give you the reason. So the new tree look like this. And so we branch 4 says word start from plus, which is correct. Branch 2 and 6 says word starts from star, which is wrong. So we do not follow this, and new tree look like this. Okay. Okay, 6 is also wrong. Sorry, 6 is also wrong because it says star here. So this also leads you to the unsuccessful because we have plus here, it does not have star. So only this node will be good, number 4. So we drop all those branches at this stage, and this will continue. Number four will continue. And once you continue number four, you replace its all E with this production E with this production rule, and this thing will come as it is because it is terminal, and then this production rule because E has two production rules, and then you replace this T with this production rule, this thing, and this thing will copy as it is. So this T will this production rule, and this thing will come as it is. And now here you again in position to decide, because don't forget that our target word is I plus I into I here. So now if you see this, number 9, we will delete that because it has 1, 2, and 3 non-terminal there. Whereas I plus star plus is already there. It means it will never generate a successful word because this word length will be bigger than our this word. If you see our word, its length is 1 2 3 4 5, and we it has 1 2 3 4 5 6 7, so its length is big, so we will drop this, we will not do this. And then if you see this I plus f plus, so it has both plus, this is also wrong, we will drop this. So this so far looks good, and this so far 11 and 12 also, so far this looks good. So might be we will drop this whole path, this path, because this is not good, and we will continue that path. Okay, so now branch 13, and look at this one. So exactly what we did. So now we replace this f with its respective production rules, and this f with here again. And here if you see this, we have princes here. Princes is not good, we will drop this. This is good so far, this has princes, we will drop this. So there is no non-terminal here, we will drop this, and we will have only one path which is good, and we will take it to the next step. So this way, at every level, you need to evaluate, and those siblings which you think that does not lead you to the successful generation of the word, you should stop them. And then once you have this one, so you generate this. Look at this one. So this is wrong, and finally we achieve our word which is required, which is I. Look at this one. So we achieve our word what we are looking, and we stop this process, that and we can say that yes, this word is member of this language, because by using the top down parsing, we are able to successfully generate this word. Okay, so that's the reason. So now what are the reasons which I just on my way explained to you? These are written here. Might be it is a bad substring. So a leaf contains a sequence of terminals that is not in the given word, or might be it is a wrong target word. So a branch that ends in a sequence of terminals which is different from the given word. So good substring, but wrong order. So might be you have something good, but you have star before and plus after that. So what we are, this is not the target word. Target word is I plus I into star into I. So this is all members are good, but the wrong order. So excess projected length might be you have all these things, but the length of the word is still more. So after that, you still have something written here. So this will increase the size of the word. So good substrings, but too many. So improper outer terminal substring. So all these are the possible reasons that which you can see, and you can drop that node and do not continue with that side, and just move with those which you think that can lead you to the successful generation of the word. Okay, then we do have another method which is called bottom up parsing, but this will be basically you have a word, and you go to from that word you want to go up and go to the next level, and go up and go to the next level and go up, and this way you can generate to the tree. But this is more complex, and this is not in the scope of this course. At some stage, if you decide that you want to do compiler construction. So then you will see the bottom-up parsing, what are the bottom-up parsing, and how we do the lexical analysis, how we do the semantic analysis and syntax analysis, all those analysis by using bottom-up parsing, and we can generate the our word there. So this, but we do have, so we do, there do exist two methods, top-down parsing and bottom-up parsing. We covered top-down parsing in this course, but this will be not in our scope, and you will do this by in the compiler construction. And that's it. I think that here we finish our chapter. So any question, guys? Any question related to this? Okay, if you have no question, I am stopping. I am the recording here.